Hey everyone. Yeah, so this sample compression scheme reductions. So this is a joint work with Idan, Attias, and Steve Hanneke. Yeah, so some motivation for our work. Occam's razor tells you that simpler explanations tend to generalize better. And one way to do this is via sample compression, is the idea of picking a subset and using that to make a predictor, right? So sample compression scheme is a specific type of learning algorithm, and it works in two steps. So the first step is you're given a data set, and you select a small subset of your data, and then use only this subset to construct a new predictor. Right. So the setting is you have an input space X, a label space Y, and a concept class. And given a data set of n points from your space, x1, y1 to xn, yn, consistent with some concept C, you have a compression function and a reconstruction function, right? So the compression takes your sequence, data set sequence, makes it into a subsequence, and then you can also have additional bits, and you want the total size of the compressed output to be small. And the reconstruction takes the subsequence and bits and returns a predictor. And the goal, the guarantee that this compression scheme needs to guarantee is that for any realizable sequence X, it's consistent on all of the samples from your data set, right? So rho, your reconstruction, and kappa, your construction, rho kappa X of X has to be Y for all XY pairs from your data set. Yeah, so I'll go through a few examples. So rectangles in R2. So your concept class can be like the concept of rectangles. So it's 1 if it's inside the rectangle, 0 if it's outside. So yeah, so here's a example data set. So you have positive points and you have negative points. And there's a compression scheme of size 4. It's to take the uppermost, lowermost, leftmost, and rightmost positive points, and then consider the bounding box of that. Everything inside the bounding box should be labeled positive, and everything outside should be labeled negative. Yeah, and here's another example. It's real valued, where your input space is in R, and your output space is also in R, just quadratics. So consider you're given all these data points. So you have a compression scheme of size 3. You can pick any 3 data points, because 3 points make a quadratic. And then the reconstruction can just make the quadratic through that. Yeah, so in general, if you have a d-degree polynomial, you'll have a compression scheme of size d plus 1. Yeah, and the last example, which is a more classical one, is the support vector machine algorithm. So our concept class here is half spaces over R2. Yeah, so the goal of SVM is to make a decision boundary that minimizes the distance, maximizes distance to the closest point. And you can, yeah, so SVM algorithm returns some support vectors, and you can reconstruct your concept just based on these 3 points. Yeah, and in general, you have d plus 1 points. But yeah, let's move on to results that are known for compression. So yeah, so in binary case, known results, finite VC dimension is equivalent to bounded size compression. Yeah, so this is just a standard definition of VC dimension. It's the largest set of shattered points. Basically, any possible labeling, any labeling is possible. And the current known bound is, in general, is exponential in the VC dimension. So classes of VC dimension D have compression size exponential in D, right? And the sample compression conjecture says that posits that there exists a compression scheme that's linear in the VC dimension. Yeah, and yeah, so this is the binary case, what's known. This is also studied in other settings like multi-class and regression. Yeah, so there are many dimensions in these settings, but in multi-class, one of the dimensions is the graph dimension, and it's a sufficient condition for bounded multi-class compression. And the current known compression size, which is uses similar techniques to prove, is also exponential in the graph dimension. Yeah, so the purpose of our work is reductions from settings like multi-class and regression to binary. Yeah, so yeah, the goal is that if the sample compression conjecture is solved, if it's true, then its proof will immediately extend to other settings. So I'll talk about the form of the results, some of the results we prove. So one of the things we prove is suppose that if you have VC dimension, and for classes of a certain VC dimension, there's a function f where there's compression size f of VC dimension. Then for multi-class concepts with graph dimension, a certain graph dimension, there's a compression scheme of size f of graph dimension times log y. So this is kind of the flavor of the results that we prove, right? So for example, if we solve the VC conjecture, then that would mean that there's a graph dimension times log y compression scheme for multi-class. And an open problem is, can this log y term be removed in general? So I'll mention later we do resolve this in certain cases, but this is still open in general. Yeah. So before we go into the proof strategy for our multi-class, I'll just talk about the list of results that we prove. So just like what we did earlier, just like what I mentioned earlier, if you have binary compression scheme of size f of VC, then you have multi-class compression scheme of size graph dimension times log y. And the log y term can be removed if you have assumptions about the binary compression scheme, like for example, if it's proper or it's a majority vote compression scheme, or if it's stable with finite labels. And we also study other settings like epsilon approximate regression, where the reconstruction returns the values up to epsilon. Yeah, and we also have similar results for adversarially robust compression. Yeah, so I'll talk about the proof idea for multi-class. So let's say we have a concept class with a certain graph dimension, and the goal is to create a compression scheme for this class. And our assumption here is that for binary classes, we have a compression size of f of VC. So our strategy is to inflate this class, so convert it from a multi-class problem to a binary problem. So for any concept C in the multi-class, we can consider the binary concept GC, which takes in x, y pairs, and it outputs 1 whenever Cx is equal to y. And it's possible to show that this class has VC dimension equal to the graph dimension of the initial class. And because of this, this inflated class has a binary compression scheme via functions rho b kappa b of sized f of graph dimension, right? Yeah, so just recall what I said right now. We can inflate this class. It has a size f compression scheme size f of graph dimension. So we can make the following compression scheme for multi-class. So given our data set on n points, we can inflate to sy, basically inflate, so all the x, y pairs, and then it's 1 whenever Cx is equal to y, 0 otherwise. And then we can apply the binary compression scheme onto the set. We know from earlier this has size f of graph dimension, but we want to encode it using our multi-class data set, right? So we can group these, the output of this compression into f of graph dimension groups. So this corresponds to f of graph dimension points from our original data set. And then additionally, for all the labels, this will require log size of y bits. So this will give us a compression of size f of graph dimension log y. And the purpose of our compression is just to give us enough information to be able to recover kappa b sy, right? So from these f of d log y bits plus the f of d points, we can recover kappa b, and then we can apply the binary reconstruction on this, right? Yeah, so this gives us a compression size of f of graph dimension log y, right? And it's possible to get better compression bounds in certain settings. So remember earlier we inflated it to the entire data set and we took all x, y pairs and compressed those. But what if we only compress the x, y, 1 pairs, right? So yeah, so maybe like a compression scheme can take in these x, y, 1 pairs, compress them, reconstruct them. So this doesn't work in general because in the reconstruction, there's no guarantees about the reconstruction. So for a fixed x, there can be multiple different y's where the output is 1. But if you assume certain properties of the reconstruction such that it's proper, then it'll work because for any element in the class, for each x, it's going to be 1 for at most y. And you can also show this works for majorities, which is actually pretty relevant because a lot of the well-known compression schemes out there use majority votes and boosting. Yeah. So assuming under special assumptions, you can remove the log y term. And I'll just talk about other reduction-based results we make, which I also mentioned earlier. So if you assume stable compression schemes plus finite label space, then we can also remove the log y term in this setting. And then we also study approximate regression. We do reduction in terms of the pseudo dimension. And we can get epsilon approximate compression with a log 1 over epsilon term. And then for adversarially robust compression, we can use similar ideas. Given a bounded size perturbation set, you can get similar compression size with a logarithmic factor in the perturbation set. And other results we also have in the paper. Feel free to take a look at our paper, but we also show a class which is adversarially robustly learnable, but has no bounded size compression scheme. So it's based on the techniques in a paper about the theory of partial concepts. And then we also via our reduction to multi-class, we include a bounded size exact compression scheme for reduction, assuming finite pseudo dimension. And these are just some open problems. But yeah, any questions?
Thanks. Time for questions.
Sorry.
Sorry.
Is it possible to have compression schemes that depend on the ds dimension rather than
That was also my question.
Can you repeat it for the?
Should I repeat it in the mic? Or is it, okay. Is it possible? We know that DS dimension is what characterizes multi-class learning. So is it possible, or what's the barrier to proving some version of this with DS dimension?
Right. That's an interesting question. I imagine if it's DS, then maybe there will need to be some logarithmic term in sample size. But yeah, it's not something we're sure about yet.
I guess you can't just have DS without a Y dependence. I guess Shirag can point to that fact. So I guess it'll be trickier to get. I guess you can have graph dimension without log Y, but you probably cannot have DS dimension without log Y.
Yeah,
So,
because there's no bounded compression in terms of DS.